Good afternoon. Today we are going to dive deeply into the cameras and stereo processing. First of all, we'll talk about the cameras themselves and the physical principles behind their functioning, and most importantly about the things that we are interested in while we are talking about the cameras themselves. The digital cameras are those exact sensors that allow us to read the surrounding almost instantly because of the very high speed of light. And technically speaking, we are interested the most in the following properties of the cameras. You know already that they could be embedded into the screen of the computer, or they could be plug-and-play USB devices, or they could be as stationary big devices on a tripod, like the one that is filming me right now. You don't see it, but it's here. So all of them have some properties in common. And by having properties in common, I mean not that they have these properties like resolution being exactly the same. I mean that all of them have certain characteristics like resolution and shutter type, and we'll talk about them in more detail later. So the first thing that we are interested in is the resolution. It could be, let's say, Full HD. Almost all the cameras that you can buy in, say, underground, near a metro station, you know, this type of stores, all those cameras are Full HD. It's pretty much standard by now, and it's hard to find a camera that has the resolution that is much less than that. So it's 1920 pixels in X dimension and 1280 in Y dimension. So this camera is providing the stream of frames of this exact size and with 3 channels of color up to, say, 30 times per second, 30 frames per second, or FPS for short. We are interested in the field of view of the camera. The field of view is a thing that you can identify for yourself if you close one eye. The angle between the rightmost area that you can see and the leftmost is your field of view of one eye. For me, it's like this. So it's nearly 140, 150 degrees, maybe closer to 140. So this is actually the idea behind the field of view. And the horizontal field of view is more important than vertical, really, because we don't that often look to the objects that are somewhere just above us in the sky. And typically the horizontal field of view, this horizontal angle, is much bigger. Some cameras have the diagonal field of view specified in their documentation or in the short form of their documentation. This is a little trick that presents the camera as if it's better than it is in terms of the field of view. In reality, if you encounter like 140 degrees in the field of view, and this is just one number, this is probably the diagonal, and the real one, the horizontal, will be 110 maybe. But usually this is even not the case, because the more the field of view is, the more complex the optic becomes. And yeah, but we will cover that in more detail. And the third thing that I am going to cover is the shutter type. It is the type of the start of the exposure, so to say. We can expose all the photosensitive matrix at the same time, or we can start exposing the photosensitive matrix row by row. And those two types of shutter have their pros and cons, and we will cover them later. On the right in the slide, you can see a so-called Bayer pattern, which is a number of light filters or color filters. Those are kind of alike to the filters that we were applying digitally, really. And we need them because in reality, in real digital cameras, we don't have 3 types of photosensitive cells as we humans have in our eyes. There is only one type of photosensitive elements, and they register only the whole, so to say, amount of energy that comes through the lens into a unit surface or onto this photosensitive element. So in order to distinguish between red beams, green beams, blue beams that come to the photosensitive matrix, we first have to install the filters. And these filters are placed on top of the photosensitive matrix, and the light comes from above, and it partially penetrates these filters so that, say, the blue filter is leaving only the blue part of the spectrum. And therefore, the corresponding photosensitive element is reading or fixing only the amount of energy that came in the blue part of the spectrum. We have to remember about the parameters auto-adjustment. I have demonstrated that already in the seminar about mask obtainment, about color-based detection. If something like that happens while you are tuning your robot or trying to make it work in certain conditions, it could be pretty annoying because you will have to retune the robot each time the camera starts to behave on its own differently than it was behaving before. So we have to, in robotics, we usually have to at first tune the camera parameters themselves, and the second we have to turn off this auto-adjustment thing regarding the white balance, exposure, gain, focus, even if it could be changed in the camera. So just keep an eye on it. One more thing is a variety of different errors that could occur during the usage of the camera. So cameras are really not perfect, and they could break, they can disconnect. We have to handle that in the code. In the OpenCV's function read, that is reading the frame from the camera, there is a flag as an output, which I usually call success. So it's the flag of the successful reading of the frame, basically. It's a flag that is equal to true if everything is fine, and if the camera has disconnected, overheated, if someone took it from the computer, this flag will be equal to false, and you can stop the processing, and you will not encounter any core dumps or shape mismatches with none type, nothing like that. Cameras are real physical digital devices. They are not Python objects, or they are not arrays. They are physical pieces of silicon, plastic, metal, and so on, and glass. And they are prone to failure. All of them are slightly different, and they consume power. You could try to touch a camera, a web camera, an external web camera that was working for some time. Probably you will feel the heat. That's because normal, typical cameras consume about 1, 2, maybe up to 5 watts. That depends on the camera, of course, but the ranges are typically like this. Let's talk about resolution in slightly more detail. Obviously, we want the resolution to be as big as possible. There are certain limitations to this parameter of the camera. First of them is the finite wavelength of the light in the visible part of the spectrum. That's maybe too silly and obvious, but let's just state it clear. These sizes or these wavelengths of the photons, they are really small. So the green light is, let's say, 500 nanometers. That is 1/2 of a micron, and micron is 1/1000th of a millimeter. So those things are pretty tiny, but still they are finite. And if we are trying to make our photosensitive elements smaller and smaller, at some point we will be not able to do so because, well, it will stop making any sense. If we make our sensors smaller than the wavelength, they will not register different waves, and that's it. So the sizes of the photosensitive elements of the photodiodes, they are in the range from several micrometers or around a micrometer up to tens of micrometers, maybe 40, 50, something of that kind. But that depends on the type of the camera, the type of the sensor itself, and the purpose of the camera. There are modern phone cameras that have the reported resolution of, say, 100 megapixels. And that could be really true in terms of the number of the sensitive elements. But it already will make no sense because of the size of the optics and the diffraction effects. So if you are filming with such a camera, very sharp edge, say razor on a white sheet of paper, very sharp edge, this edge will still be blurry. And you can try it for yourself, and it will be blurry. The gradient between the dark and the white will be for, I don't know, some number of pixels. And if it takes 30 pixels to transition from dark to white, does it really make sense to introduce more and more pixels to that? I don't know. So that's more of an marketing thing here in terms of the increase in megapixels to crazy numbers like 100 million, 200 million, I don't know. Another limitation is the bandwidth. So we have to transfer those frames somehow to the processing unit. We have to have the interface between the camera itself and the processing unit. The processing unit have maybe multiple cores, or maybe just one core that is very fast. So this whole system has to have a lot of very fast memory and so on. So processing the frames from the cameras with high resolution is complicated, and it requires lots of computational resources from the whole system. We have many limitations in terms of the resolution, starting from the computational powers and up to the physical limits of optics, the quality of the lenses, the wavelengths. But of course, we want our cameras to have the highest resolution possible under all the circumstances in order for us to see the tiniest parts of the scene that we are filming. The effective resolution of a human eye, if we account for the movement of the eyeballs, is nearly 100 megapixels. So that's more of an approximation than an exact number, of course. But still, it makes sense in terms of the angular resolution of our eyes. While in the digital cameras, the density of the pixels on the whole matrix is uniform, in our eyes there are some special places or some areas where the density of the photosensitive elements is considerably higher than in the rest of the retina. And exactly this spot, this so-called yellow spot, we are trying to point at, let's say, a book when we are reading. We are reading with the most sensitive areas of our retina, and that makes sense indeed, because we can spot the proper details and then take a closer look at them. Regarding the field of view, well, we have already talked about my field of view, which could be found out like this. And we also have another one, which is the stereoscopic field of view. Try to think for yourself, how can you measure that? How can you measure the area that could be visible in stereo? That could be done by first finding the leftmost area that you can see with your right eye and the opposite from here. So this is the area where I see all the objects in stereo. Outside of this area, I don't see objects in stereo because I can see them only with one eye, and that's because of the presence of my nose. A funny thing about the nose is that humans are not really much aware of the presence of their nose in frame, in sight, before you tell them. So probably now you notice your nose, and you can easily tell that it distracts the vision. And if you would have no nose, then the area of the stereoscopic vision will be much greater. But, well, that's enough for us to see only the objects that are just here nearby, and we don't really need the objects that are behind us to be in stereo. And if we need, we can rotate our head with the neck, and that's the extension of the same mechanism that allows us to point our eyeballs at certain points, in some sense. Humans have really good visual perception system, and while constructing the robots, we tend to move towards the same goals and same directions and same properties as are present in the robots. One modern trend in robotics, and in particular in humanoid robotics, is the wide-angle cameras. I'm talking primarily about the humanoid football and other types of robotics sport. Well, in industrial applications, of course, the field of view is defined completely by the problem that is being solved. And here in the frame you can see that this image was taken with a thing that is commonly referred to as fisheye or fisheye lens. This is a wide-angle lens that allows for capturing the objects that are, so to say, very far to the right and to the left. We use that because it allows the robot to rotate its head with much smaller angular speed than it was before. Before that, we were using narrow-angle optics, and the robot had to perform crazy movements like this all the time, and it had to construct a compound picture of all of that on very high rates, so that was not very cool. And the ball was inside of the robot. The ball is visible for just a fraction of the whole time. And by now, because of this type of optics, we can capture the ball for the majority of the time. And while standing somewhere in the middle, in the right orientation, this stereo robot is capable of seeing both his goalposts and the opponent's goalposts. So the wide field of view is a big advantage. And I think that many other teams will orient towards that in closest future. On the other hand, there are certain cons to this concept. One of them is the varying pixel density. What do I mean by that? By that I mean that if two objects are really close to the viewer, they're somewhere right here, I can see them in great detail, and if I move these objects towards the border of the frame, they will be at first distorted, but that's fine. But another thing is that because of this whole nature of the wide-angle optics, they will have less detail in them. The same objects will be represented with a much smaller number of pixels. But, well, that's better than nothing, and we can account for that in the training of the neural networks, and that's fine. And another thing is the fisheye effect itself. So I was talking about distortion, and here you can see that all the lines here are not really straight. That's because of the fisheye effect itself. The next thing is the shutter type. And as I told you previously, that is the difference between exposing the whole matrix at the same time, which is global shutter, and it's on the right, and exposing lines one by another, or, well, some of the lines, some of the rows of the matrix could be exposed simultaneously, but starting at different points in time. And here on the left, you can see the example of what could happen if you try to film a rapidly moving object with a rolling shutter camera. Probably you have seen that with your own phone or camera or whatever else while trying to film moving objects, rotating ventilators, some birds flying, whatever else. And this happens because different parts of the scene are basically captured at different moments in time. And in such a dynamic application as robotic football or any kind of dynamic robotics or autonomous robotics, is better to say, with these types of applications, we usually have to have all our lines straight. So in robotic football, it's better to have the global shutter type cameras instead of rolling type cameras. The consequence of that is the dramatic increase in the price of the cameras. They tend to be, so to say, industrial grade cameras, so they cost a lot. And another thing about them is that they can consume more power than regular rolling shutter cameras. Rolling shutter cameras could be installed in the laptop. So here I have a normal web camera, which is very tiny. So all the optics, all the sensor and everything, the whole board, it's all like this thing. This thin, it's very small, and I'm not sure that it's possible to create such a camera with the global shutter technology. And one more thing is the lower photosensitivity of these types of cameras. But still we use precisely them because they give us the ability to capture the scene that we are filming with very low exposure time, and all the straight lines continue to be straight after we have filmed them. Let us consider a geometric model of the camera. So here in the frame you can see this is the object that we are looking at. Let's imagine how this object is going to be represented in the camera. So this is the photosensitive matrix. This is the middle of the photosensitive matrix. This is the optical axis. So try to recall the geometrical optics. And this is the focal point. And the surface that is somewhere over here is the focal surface. The camera is looking to the left top and inside of the slide. And here, according to the rules of geometrical optics, we can see that this object with the coordinates x, y, z will become this point with coordinates u and v in the camera matrix. The parameters of this transform are written here in the form of a matrix A, which is called a matrix of camera calibration, or intrinsic camera parameters, or camera model. So these four numbers are fx, fy. Those are the coordinates of the focal point measured in pixels, in units of x and y axis. And they are, in the general case, not the same. And cx and cy are the coordinates of the middle of the photosensitive matrix, or the principal point. And it's not exactly in the middle of the matrix itself. Because of the optics, the lenses are not perfect, and the whole placing of the whole arrangement of the photosensitive matrix and optics and all the rest could be slightly off. So we have to find out those parameters with the so-called calibration procedure. The thing that we were talking about previously is the distortion. And it requires for the camera calibration as well. So here you can see the ideal chessboard, so to say. This is the chessboard with one type of the distortion, and here's with another type of distortion. The right one is not as common as the second from the right. And this one, this barrel distortion, is exactly the one that we encounter with the fisheye cameras or wide-angle cameras. So we have to have a way of somehow transforming this picture into the leftmost one or this one. In order to do that, we capture a lot of images of this real physical chessboard, and out of that we can solve the, well, OpenCV can solve for us some optimization problem, and the output of this optimization problem will be the conglomerate of different characteristics of the optical system. As an output, we will get the coefficients of the distortion, series expansion, and also the camera calibration parameters themselves. How can we understand where in the physical world are the objects that we are filming? So let's suppose that we have already solved the problem of computer vision or the detection problem. Let's say that we have detected the objects already, and now we are interested in finding out where do they belong in a robot's frame. Where are they physically in the meters, not in the pixels? We have to do two things. We can consider this whole system as two triangles. The first triangle is in the physical coordinates. So the first point is let's say, an intersection of the optical axis with the surface. The second point is the object, and the third point is the focal point of the camera. And the second triangle is the focal point of the camera, the object as if it's visible on the matrix, and the principal point of the matrix itself. So those two triangles are similar to each other in terms of the proportions and angle, but they're measured in different units. One of them is in meters, and one of them is in pixels. The second thing that we have to consider is the geometry of the camera displacement in the world itself. We know for sure that the height of the robot is this and that. Let's say it's 70 centimeters. And from the proprioception, we know precisely the positions of all the limbs of the robot. We know the inclination angle of the neck, and we know the rotation, the yaw angle of the neck, as well as hip, knee, and everything else. We can calculate, assuming that the feet are standing straight, we can calculate precisely the angle of inclination of the main optical axis. We can, as you can see here in the frame, it's marked as blue. We can calculate where does the main optical axis penetrate the surface. So we can find out, using our previous topic or previous considerations, the calibration matrix of the camera itself. We can calculate the position of the object over here, because we know first how the main optical axis is positioned in the world. We know the height of the robot, so the angle that is here could be calculated from the kinematic model of the robot at a given moment in time. And on top of that, we can use the information about the position of the object in the image, in the frame. And since we know the calibration matrix of the camera, we can calculate the corresponding distance to the object from this point, from the intersection of the optical axis and the surface. This is the way in which the monocular vision could allow us for the understanding of the position of the object in the real world, not in the frame, but in the world. Well, here we have to assume that the Earth is perfectly flat, and that is not always the case. So if we will move from the problem of football to another problem, let's say hiking or mountain biking or whatever else, we will have to consider the world not as a planar model, but as a full model, as a real model. So we will have to be a 3D surface. That's a different problem. So by now we have half of our robots with mono cameras, and it works like this, and it's fine, basically. Another thing is that we can use the size of the object as a reference if we know that already. So here on the left, you can see the ball, and we know for sure that the ball is of certain size. It's a souvenir ball that you can buy in any part of the world, and it has a specified diameter. So we have finding out the diameter of the ball in the frame. We can extract this information and use it to find out the distance to the ball, I mean physical distance. There are in total 2 different ways of dealing with these problems, and the first one is slightly more general, and the second one could be more precise. But if you are interested in detecting only the certain types of objects, like those balls, it's perfectly acceptable. The next topic that we are going to cover is stereo, but that's for the next part of the lecture.